Okay, this is example 2. So we want to find the general solution of this differential equation. And if we try to separate the variables, it's not going to work because this equation is not separable. You can try, but it's not going to be separable. And you can't use the integrating factor technique because this is not a linear first order differential equation. It's a first order differential equation, but it's not linear. So again, this is where our substitution method comes in handy. And the first thing that you want to try is, in the previous video, right, I talked about what a homogeneous first order differential equation was. So let's see if we can maybe write that in that specific form. So let's solve for dy dx. So I'm going to divide both sides by 2xy. Alright, so all of this guy. So we get our nice 1. So dy dx is equal to, and then we can split these guys up. So let's see, we get 2 x squared over x is just x over y plus, let's see, 3 halves y. Oh, actually over x. Over x, right, because there's an x in the denominator. And I'm going to just rewrite this. And I'm going to write my 2 out here, and then I'm going to write x over y plus 3 halves, and again, this is really y over x. And so I'm thinking of substitution just by looking at those fractions, x over y and y over x. So now we can make the substitutions, since this is actually a homogeneous first order differential equation. So I'm going to let, right, this guy is going to be, I'm going to let x over y be my, actually y over x, I'm going to let it be v. So let v be y over x. So we know we're going to use this equation later because we want it in terms of a function of v and x. And if we solve for y, right, just cross multiply, we're just going to get vx. And again, we're going to be using this equation. And now we want to take the derivative of that guy. That's how we get our third equation. So this is just going to be the d dx of y, which is really just dy dx, and d dx, well, let me just go ahead and write it, d dx of vx, right? And notice again, we're just going to use, this is the product rule. And so if I move this up, oops, so I'm going to have dy dx equals, and again, just using our product rule, let's see, we're going to have the derivative of, let's see, x, which is 1 times v plus, and then x times derivative of v, which is just dv dx. So we have our third equation. And actually here, since we have, so I let v be y over x, but this is not v, right? This is x over y. This is the reciprocal. But we can, write a relationship between those two. All right, let's maybe write it over here. So since v equals y over x, okay, well, we know 1 over v is just x over y. So we have this extra relationship that we want to use. And I should have a division bar right there. Okay, so now that we let v equal y over x and we found some relationships, let's substitute this information into our original equation to get it in terms of v and x, right? Our g of v and x. So let me move this up, and let's see, actually I want to make sure you can see the original one. So this was our this is our dy dx. So let's just start substituting. So what is my dy dx? Well, it's right here in terms of x and v. So I can write, okay, let me just write the equation. So 2x over y, 3 halves y over x. Okay, so let me just, okay, dy dx, what is dy dx? It's v plus x, right, dv dx, or v prime, equals 2 times x over y. Well, my x over y is my 1 over v, right? It's this guy. So that's times 1 over v plus 3 halves times our y over x, but we called y over x, right? We let that be v. So I can just write v. So again, I just want to emphasize the goal, right, at this point was to get a function of v and x, right, from our original f of xy, right? So or maybe I should have written this first, but right, we're transforming these guys. Okay, so we can do some algebra and just simplify this expression. So let's go ahead and just make an arrow here. So I'm going to go ahead and solve for x dv dx, right? So I'm going to bring that v over to the right hand side. So this is really 2 over v plus 3 halves v, and then I'm going to subtract that v. So I'm just going to use some algebra here, just basic arithmetic. I'm going to add and subtract these fractions. So we know our common denominator, right, should be 2v. And so we have, let's see, multiply the first term by 2, so we get, we get 4 plus 3v squared minus 2v. And so if we simplify that a little bit, we get, let's see, am I missing? Oh, I'm missing times 2. That was, this part was times 2v, so that should be 2v squared. And then I get my v squared plus 4 all over 2v. Okay, so now let's try to separate our variables after this transformation. So I'm going to multiply both sides by dx, so I get x dv equals, let's see, v squared plus 4 over 2v dx. And again, x's with x's, v's with v's. So I'm going to divide both sides by x. So I have 1 over x dx on this side. And then I want this guy to be 1, so I can just multiply by the reciprocal to both sides. And I just get 2v over v squared plus 4 dv. So we were able, right, able to separate the variables, right, after this substitution. So now we can integrate both sides. And notice the familiar, right, integral. So the integral of 2v over v squared plus 4 is the natural log of v squared plus 4, right, because the derivative of this guy is 2v, right, over itself, right? This is your f prime over f of x, or f of v in this case. And then the other side is just a nice natural log of the absolute value of x plus, plus c. The book uses ln of c, but eventually we're just going to write c, or if you want to call it k again, or a. So we were able to integrate We have these natural logs on both sides of the equation. And the reason the book wanted to use, again, usually you add just some c, some constant of integration, but they wanted to add this ln of c because it's still some arbitrary constant, because then we can use the properties of logarithms, and we are going to exponentiate both sides. And when we exponentiate both sides, right, these are inverse functions, so we're left with v squared plus 4 equals, and if you want to write, let's see, just to get technical here, we have e to the ln of c. Okay, so we have v squared plus 4 equals, and then we're just left with the absolute value of x times, okay, e and ln become 1 times c, so eventually you just have c. And so this is just, right, c times the absolute value of x. And again, our original differential equation was in terms of x and y, so we have to go back to x and y. So let's maybe, oops, all right, substitute, right, or back substitute if you want to say, right, to your original, to x and y's. Okay, so what was our v? Our v was y over x, right, and then I'm going to square that, plus 4 equals c times the absolute value of x. And then, of course, we can just write x squared over y squared plus 4e. I have this, and then I'm just going to multiply y squared to both sides. So x squared plus 4y squared equals times x squared. Okay. And actually, this should be x squared. So if you try to solve for y of x, you're not going to be able to define it explicitly. And so again, this is on page 62. I just wanted to write down some intermediate steps since the book skips quite a few steps. So I encourage you to read the paragraph right below this guy. It explains how, the solution that they got. And why it should be, positive and negative, because eventually you're going to take the square root of both sides. If you have any questions or you're not sure what that paragraph means, please send me an email and I'll go over it.